Hello, welcome to my channel. This is Vale and I'm not going to be in the video today, and I'm not going to be introducing any new topic because this is a continuation video to my last uploaded video, which is on a buffer overflow on the stack and on how to actually override values in memory addresses to alter the execution flow of a program. So you can see that I have the exact same program as I had yesterday, but only with one thing changed, that is in place of 8, where I had taken exactly worth of 8 characters length variables, I just increased that to 32 because it's very hard to find shell codes that is that small. So anyways, as you can see the program, if you are actually a first time and you do not want to go to the previous video, well, here it is that I have just taken 2 variables. I'm just printing the first variable, and for the second variable I'm just taking a user input, and that's it. The whole job of the program is just that. What I wanted to do in the previous video, what I actually did in the previous video, was change the execution flow of the program such that even if this bypass function was never called from main, I still managed to call bypass via reverse engineering the program and then overflowing the stack such that the bypass function did actually get called. So anyways, today what I'm going to do is what I promised on the previous day, is that how can I actually execute or get an interactive shell from this innocent piece of code such that I can do anything from that shell, only in case if I have a root privilege, which I'm not going to discuss about today. So if I just remember that on the last video I left you with implementing this slide practically, right? So what I did was in place of scanf, that is when I was prompted by my program to input a value, I gave this string or something like that, such that some of the string actually overflowed to the next variable, and on the other section what I did was I used the same exact vulnerability that I gave a value for variable 2, but half of the value reflected in the location for variable 1. So this is actually a pretty basic explanation of a buffer overflow on the stack. So I use the same exact vulnerability to give a string that is exactly of this size, which was very manually and very programmatically coerced. So when I gave this string, what happened was the first 8 ones stayed on its actual place where it was intended to. The 8 2s went down to the other variable's location. The A overflowed the old location for the old base pointer, and this 507th address was overflowed to the location of the old instruction pointer, and that's how we were able to call this function, which was actually not intended for the program to call. So I'm going to use the same exact vulnerability today to actually execute a shell, which is not a function that we know about that exists right here, but in this case, in this today's video, what I'm going to do is execute a shell. Nice. So as you can see that I have a new slide for you today, and I'm trying to explain what I did here. So let me just take you to the previous slide, and as you can see that in the previous video I supplied this string, right? So what if I supplied a string version of the whole thing that is now residing on the stack? So let me just say to you what I am actually doing. So what is x90s? You can see the x90s here, right? So what is x90 exactly? So if you know Python, you know there is a function called pass. What it does is it basically tells the compiler to not execute anything or not to do anything until and unless it hits a new part of the code that is actually worth of doing something. So let's say I have a basic program. I can say like say I have a basic program that, for example, if 1 equals 1, then maybe do something, and else, let's say, pass. And there I have a code, maybe there is a function called, hello. So what it's going to do is, if 1 is equal to 1, it will do something, else it will basically come to pass, but the keyword or the function pass basically means do nothing. It will immediately come to the next part, which is actually an executable, or which is a function. So in this case it will call hello. So what if I did the same with maybe multiple passes? So these 4 passes actually mean nothing. It means that the program will go for 4 more cycles, but it will ultimately do nothing. So the difference between 1 pass and 3 passes is that the processor will actually try to execute whatever is written on the next lines, but it will ultimately realize that it has nothing to do because we are just doing nothing on the else section of the code. So to the compiler, x90 works similarly. So x90 basically means don't do anything. So after x90 we have shellcode. Now why I actually did so much x90s, I'm just going to explain in a very few seconds. So let me just tell you what a shellcode is. So the shellcode is basically a couple of hex characters that when assembled works like a small program that maybe just calls a shell. So if you just open up the terminal in your Linux and maybe say execv and in the brackets you say /bin/sh. So what it does is it's going to basically execute the shell for us. So this exact piece of code has a meaning to the compiler, right? So it, as we already know, that the compilers only understand in binary, or we can view that binary as hex. But whatever it is, this shellcode is a basic hex version of what I'm trying to do in a computer. So in this case, it's going to do the same thing that if we just go into Linux and write maybe /bin/sh, the same thing is converted into a shellcode, and the shellcode in my program will basically call the same thing, that is /bin/sh. So that is it. So the shellcode is just a piece of executable code that does something. Now, why there are so much x90s? So the main reason that we are implementing so many no operation characters here is that we cannot be exactly sure of the location where the shell code starts from. We can actually try to figure that out. That is not of a problem, but in many of the cases, due to some randomization that happens on the OS, due to maybe the way GDB works, or due to sometimes how the shell works, maybe we do not know the exact size of the stack, or if there is some extra information that is kept on the stack. So we cannot sometimes compute on which exact memory location this shell code is starting from. So that's why if we do this much x90s, what happens is when we actually overwrite the old instruction pointer's address to maybe say 0000000, which we know is this memory location right now, so in this case which is just this block of the memory location or the stack right now. So what happens is it goes to 100, which starts from here, and it just basically does nothing because all it can see are a couple of x90s. So what exactly happens is it goes to the first x90, it does nothing, so it moves on to the next x90, and it keeps on moving and moving and moving until and unless it reaches the first character of the shellcode. So as soon as it reaches somewhere that is actually something to be done by the computer, it starts executing from that exact region. So from starting from that exact region to this exact region, we have our shellcode, right? So as soon as this shellcode exactly gets executed, then we can actually have the shell. If the shellcode was meant to shut down the computer, then the computer will shut down. If the shellcode was some kind of backdoor, then the backdoor will try to connect to a different PC or open up a bind port. Whatever the shellcode means, it will start. So it might be anything. So the meaning of the shellcode exactly doesn't matter in a typical example of a Stack Overflow, but the shellcode is just for an example that as long as we can manipulate the return address on the stack, we can redirect the instruction pointers to start executing stuff anywhere we want. So I'm just going to go to my VMware and show you hands-on exactly what I'm talking about. So as you can see, I'm in my Kali Linux right now, and I'm just going to open this up and just show you that this is the shellcode that I have downloaded from the internet, and this is the exact URL for the exploit. I will just try to provide this URL onto the about section of my video. Anyways, so this is the shellcode that I was talking about. The job of this shellcode is simply just to open up a shell prompt. That's it. Now, when you are downloading or searching these shellcodes on the internet, you need to very much remember or exactly know the amount of bytes that it actually takes, because in a case of, or in a scenario of shellcode exploitation within a buffer overflow experiment, you need to be very precise and count every step of what you are actually doing. So remembering this 24 bytes is pretty important. Anyway, so this is the shellcode that I downloaded off of the internet, and I am going to go over to the same program. Now you have to take care of something right now. So first of all, you need to actually disable Aslr for your system. So we need root permissions for that. So doing this will actually disable Aslr until and unless you restart the system for the next time. So when I'm doing this, the value for randomized VA space will go to 0 from the current value, which is 2. So anyways, that's how I can actually terminate or temporarily disable Aslr protection from my computer, because you can do the same things with Aslr on, but that's a tutorial, or that's a topic for another day completely. So one thing is that, and another thing is you need to exactly compile your executable in the exact way. So I have actually copied and pasted right here. So FNO stack protector is basically, it's stopping the stack from being protected. So the -z exec stack, what it does is it actually enables executables within the stack, and I don't know exactly what NoPy does, so sorry for that. Anyways, so this is the program, and as you can see that it's pretty much the same thing. So if I just run mf and maybe give something, maybe give something, I don't know. So I just need to delete the space because scanf treats it as end of the sentence. So give anything, and whatever I do, we get a value for the variable 1, which was hard-coded to hello. Anyways, so I'm now just going to go to GDB. Now let me just stop once here and say this again, that this is the continuation to my previous video about stack overflows or buffer overflows in the stack. Now if you're new to assembly, you cannot actually understand a lot even in my previous video. So what you want to do is, first go to Google, study anything about assembly, get a basic idea about assembly or machine instructions by itself, then come to the first video of this series that I made that is on fairly exclusively made on stacks. So after you learn stacks, go to the next video of mine, which would be reverse engineering basic tutorial. So there is many things about assembly and on how to actually remember or note down the execution flow of a program and how to proceed reverse engineering. So that video is completely about that. The next video, which is basically the previous video from this one, which is on basic stack overflow examples, and then come to this video, because if you do not know any of these what I just have talked about, then watching these 4 videos is gonna be good for you. Anyways, let me just go ahead and start the tutorial. So I'm just going to be starting GDB memf, and I'm just going to open up a terminal on the side because I need it pretty much. Anyways, so first up, what I'm going to do is just set the disassembly flavor to Wintel and just run the program for once, maybe, whatever, I don't care. So now what I want to do is set a breakpoint at main. So when I just type in run, I can actually stop and see on each cycle or on each instruction what is exactly happening. Now let me first calculate something. Now in a practical program, you might not exactly know that what is the exact number of bytes, or what is the limit of the exact number of characters that is allowed for each variable, what is the exact space on the stack that will be set on the start of the program, and how many values or how many variables will the stack actually have. So you cannot know all of these in a practical program, but for the ease of understanding today, I particularly know, right, that we have 2 variables in this program that is assigned 32 bytes each. So we have a total of 64 bytes just for the variables, and if we just add the location or add the space for the previous base pointer, which is again 8 bytes, and the previous instruction pointer, so that is also 8 bytes, that makes it, so if I just go into the calculator and make you see. So 64 bytes worth of two variables plus one base pointer's location and one old instruction pointer, I get 80 bytes. So I know my stack will exactly have 80 bytes worth of free space to work with our variables in this present stack. Nice. So what I'm trying to do is, first let's figure out the exact offset. So figuring out the exact offset has already been taught on the previous video, but I'm still going to do it again because this is pretty much everything, or the main important thing for a buffer overflow. So if I just calculate, so 64 plus 8 plus 8 is what we are looking for, and this is the exact orientation of the stack we currently right now have. So if I just go and just print out something, so for example print, or just let me do Python -c print 64 A's, then print let's say B for the RBPs, so A plus C 8 times again. So we should exactly get to see the values of A and B and C, and what are the locations that these values stay in. So for that, let me just copy this up, go to my here. So here what I'm going to do is I'm going to run this program, but this time with the exact copied and pasted command, Python command that I just made up right here. So if I just press enter, yep, and just go on some instructions. So if I just see if I have crossed scanf, yes, scanf is at 11C6, I'm at 11D9, so my old instruction pointer's location should have changed by now to C's. So let me just see info frame, and you can see I have all 43s in my old instruction pointer's address. So I know that this orientation is perfectly okay, right? So now we have to provide the shellcode that will be within the stack. So for example, if I just do display with display addresses, so maybe just say WX, maybe I want 50 of them, so RSP. What? Okay, sorry. So as you can see that we have 4 here and 4 here, sorry, so 4 for the 16 and 16 for the 64. So we have exactly 64 bytes worth of A's right here. Then we have 8 bytes worth of B's, which is in this case should be the old value of the base pointer, and we have 8 C's, or 8 bytes worth of C's, which should have been the old instruction pointer's value. So what we need to do is we have to supply the shellcode that will reside somewhere within here, right? So how can we actually do that? Now let me open up a simple mousepad like this and say that we have a shellcode, right? So let me just close these things up. Nice. So we have a shellcode that is exactly 24 bytes, right? So what we want to do is we have 24 bytes worth of shellcode. So if you remember from the picture or the slide that I have shown you, we need to actually pad the whole shellcode with a couple of knobs, so we have enough space at the start and enough space at the end, so the compiler cannot go wrong right here, right? So if I do it in the start, if I implement a couple of knob sleds or a couple of knob instructions in the start, then we do not have to worry about the exact starting address of the shellcode, because whatever it is, the return address is going to be coming or going to be pointing on a couple of knobs, and when the knobs are done with, the shellcode starts executing automatically. And for the end section, what happens is that after the leave instruction is executed, we already know from the first video of mine or from the definition of stacks that when the leave actually gets executed, the whole stack is deleted, right? or actually deleted is a mistaken word. What happens is the RSP is given the value of RBP. So RBP is right now somewhere, maybe this is the RBP, right? So this should be the place for RBP. So what happens is RSP is given the value of RBP, and what happens is both the base pointer and the stack pointer is now pointing at the same exact address, and in the shellcode there might be a couple of push and pop instructions. So when that happens, there sometimes is a possibility that the shellcode actually gets overwritten with itself. So we need to pad both the ends of the shellcode, that is the start and the end of the shellcode, with some pads, so the compiler doesn't go wrong executing the shellcodes. So what we need to do is, we have 24 bytes worth of shellcode, and we need to figure out that what is the number of total characters that we need to overwrite, given that the shellcode is residing somewhere in here. So the total number of characters that we figured out previously was 80, right? So 80 is the number of total characters, including the previous base pointer and including the previous instruction pointer, that we need to overwrite to actually overwrite the instruction pointer. But 80 includes the instruction pointers, so we need to decrease or decrement 8 from it. So 72 is the exact offset, or 72 is the exact number that excludes RIP, but is the exact number of characters that we need to overwrite the whole stack excluding RIP. So we have total 72 bytes worth of overflow material, right? So now the 72 doesn't exactly include the 24 bytes shellcode right now. So we know that our shellcode is worth 24 bytes, right? So if I just decrement 24 from it, we get this number 48, and 48 is the exact number of pads that we can do, because the 27 is useless here right now, because 27 is going to be the exact space that the shellcode will take to reside anywhere in the stack right here. So let me just go here on my mouse pad and actually figure out the orientation. So 48, let's say we divide 48 by 2 and pad the numbers from both of the ends. So 48 by 2 is 24. So what I'm going to do is, we need, so if I just say orientation or structure is the better word. So we need 24 pads plus 24 byte shellcode. So then again 24 byte pad plus, so this makes 72, right? So 24 plus 24 plus 24 makes 72, and we already know that the 72 is the exact offset, or the exact number we need to overwrite the stack with to reach RIP. So now we have actually, in this section, we have actually reached the location where we write anything after this will actually go over and overwrite RIP. So if I write here, let's say 8 bytes of RIP. Nice. So if I just make this happen with a little Python code, so let's say Python -c print. Now I'm just going to say, let's say a 24 times, so 24 times plus, let's take B for shellcodes, so B times 24. Again, for the pads, A times 24, times 24, and this is going to be the exact, now we have actually gone through the exact number of bytes or exact offset that we need to override before we can actually change the RIP. And what I'm going to write after this plus, whatever I write is going to be overwritten to the old RIP's location, alright? So if I just go and say maybe D, so D is 44 in ASCII, so D times 8. So if I actually print this out and run it with my program, and if all the D's are on the instruction pointer's address, that means that the orientation or the structure of the whole argument that we are going to supply for scanf is perfectly executed. So D times 8. Now let's execute this, alright? So run Okay, one thing to tell, if you remember from the previous video that I actually copied and pasted the result of a program, something like that, and then copied and pasted onto the scanf section of the program. Now you have to remember something, that on that exact case the ASCII characters were printable, so I actually was able to copy and paste, but majority of these type of things when converted to string is not actually printable characters. So you cannot copy those non-printable characters from a terminal and paste that on another terminal. So you cannot actually do that. So that's why I'm directly feeding the results to the scanf, so I do not have to copy or paste at all. So if I just go ahead and run this and get some point where I am out of the scanf section, so this as main, sorry. So if I do that, I can see that I am out of the scanf. So if I just view the stack, I should see all the D's in place of the old instruction pointer's memory location. So info frame, nice. So we can see we have all the 8 D's in place of the old instruction pointer's address, which means that our offset calculation or structuring the program like this actually paid off. This was perfectly okay. So the last thing we need to do is to figure out the exact address from where the A's start from. So if I just go and say maybe, sorry what I'm typing, so if I just do this, we can see that the A's start from the perfect address, that is FF7 FFFFFFE170. So if I just go a little bit back, so maybe say RSP minus 16, so we can have a better look at that. So yes, from the RSP minus 16, which is E160, the offset is E160, so we have some variables that we do not have any idea for why they are there. All we know that the A's start from the exact address 170, right? So we need to copy and paste that and keep note of what I'm doing. So this is the exact address that the A's start from, and let me just actually proceed with the program and see what exactly happens. So we are getting a segmentation fault, and of course that we should get that. So if I just go and see this, but this time I'm going a little bit more, because now the RSP's value and the base pointer's value is basically the same. So if I just go and say maybe minus 500, we can still see all the A's. Are they here? I don't think so. So minus 200, so nice. So you can still see, if I find them, yes, the A's are still starting from 170. So we know that the program actually exactly keeps the stack in the way that it previously did when the stack is even erased, right? So the stack has been erased right now, but we can still see that the values are still on the stack, which is just waiting to be deleted by some other program that is going to be run next. So we can pretty much confirm that E170 is the exact address that our stack's variable starts from. So in this case, this should be variable 2's location right now. For 32 bytes, it should be for variable 2. For the next 32 bytes, it should be for variable 1. So we are pretty sure that E170 is the address. Now I am going to actually generate the whole actual shellcode that we are going to destroy our stack with. So let me first convert this to little endian. So if I just delete this, and it's easier to view like this. So if I just go x7f, sorry, x70, xe1, xff, 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 x7s, 7f is the address that we are going to overwrite the old location of rip with. So we just keep that in mind. Now I'm going to generate the same thing right again, but this time with all the knobs and exact shellcodes and this exact address, because we have confirmed previously that this is the exact structure that we should implement to do exactly what we want. So 24 pads shellcode, then again comes 24 pad, and lastly the 8-byte rip. So Python -c print. This time what we are going to do is print a couple of x90s. So these are all NOPs, or no operation instructions. So print x90s for 24 times, because we are going to use nops to pad both the ends of the shellcode. So x90 times 24 plus here the shellcode comes in. So where's the shellcode? Here's the shellcode. So we have the shellcode right here. So then we are going for the shellcode. Let me just maximize this for a second. So 24 bytes worth of padding with nops, then the 24 byte shellcode plus 24 nops again. So x90s times 24 plus the return address, which is this one. I have pre-computed this right here, so this is going to be pasted right here, and this is the whole command that I should wish for. And now let me actually copy and paste this in a real file so we can have an interactive shell in GDB. So if we do get to go in the shell, so what I'm talking about is if the exploit actually worked, then the exploit is going to be started and finished immediately, because it will act like an end of file. So that's why I'm still going to keep the shell interactive, and for that to happen I need to actually print this into a file. So I'm just going to paste this and maybe store this into a file called buff.txt, right? So let me just see what's in buff.txt. This should be all non-printable characters, as you can see. Nice. So I really hope that this works. So again, let me just see if the orientation is perfectly okay. So 24 times x90s, then the whole shellcode, then again 24 times x90s, and then comes the 8-byte RIP. Let me just calculate this all again one more time just to be sure. So 24 times pads plus 24 byte shellcode plus again 24 bytes of padding plus 8 bytes worth of RIP. So this makes it 80. Perfect. So 80 is the number that we are looking for. So let's execute this right here. So we have everything of this within this bof.txt, and I'm going to supply the whole text file as an argument right here, of course interactively. So if we do get a shell, we will actually not get terminated, but we have the interactivity still alive for us. So let me just delete all the breakpoints that we have. So that's how we are directly going to go over to the program and see if this actually works. So let's go ahead and say run, and within this we have to actually do cat buff.txt, and so this is the hyphen character that is going to still give us the interactivity in case that we do get the shell. So if I just hit enter, yep, we want, okay, so you can see that variable 1 is showing me this non-printable couple of characters. So you can see that it's saying us that process 12795 is executing new program called user, that is under /user/bin/dash. So I don't know if I got the shell, so let me try and write who am I. If I hit enter, you can see that I have actually got the shell. So if I go present directory, I get home Kali desktop. Nice. So for example, we can also do cat etc password. So you can see that I have actually got this. So actually you can do pretty much everything from here except of root commands. So in that case, if you want, then you can actually execute this as root and get a root shell. So I guess that will conclude my class right here. So until and unless I come up with a new one which is more interesting than this, which is more experimental and worth a lot of knowledge again, so stay tuned for that. I hope you can understand what I'm trying to teach. So until next time, goodbye, thank you for watching, stay tuned, and I am hoping that this video is going to be the end of this current series that I have been doing for the last couple of weeks. So until next time, goodbye.